Hello, everyone. Welcome to today's Laser Focus World webcast, How to Model and Simulate Fiber Amplifiers and Fiber Lasers, sponsored by VPI Photonics. I'm Justine Murphy, Senior Editor of Laser Focus World, a part of Endeavor Business Media's Design and Engineering Group, and I'll be your moderator. And now let's meet today's speakers. Chris Maloney is the Director of Business Development and Managing Director of U.S. Operations at VPI Photonics, where he brings previous modeling and simulation experiences from his time working in the semiconductor industry at IMEC. He has a Master of Science degree in Microelectronic Engineering from the Rochester Institute of Technology and an MBA from Messiah University. Chris is currently president of the Rochester section of Optica. And we also welcome Piotr Novik, who joined the VPI Development Center as a modeling engineer in 2018, and in 2021 moved to VPI Photonics in Berlin, Germany as an R&D engineer. He conducts research on VPI component maker fiber optics and VPI toolkit QKD development, including different QKD protocol implementations, and also creates simulation models of devices required for quantum key distribution. During his work at VPI Development Center, he obtained a master's degree in theoretical physics from the Belarusian State University. Hello, Chris and Peter. Welcome. The floor is yours.
Yeah, thanks, Justine, for that nice introduction. We'll get started today. I have a brief outline here just to go through, so you have an idea of what to expect for this webinar. So I'll get us started with a brief background about VPI Photonics and why we're here today, and then Piotr will join us for a technical discussion around our simulation framework, get into the modeling of doped fibers, and run through an application example of a ytterbium-doped high-power fiber laser. And then we'll discuss undoped fiber modeling as well, and talk about another application example of a remote optically pumped amplifier, which utilizes both undoped fiber and doped fiber. And we'll actually show that in a full system-level simulation as well. So again, yeah, thanks everybody for joining today. So why are we even here talking about fiber amplifiers and lasers? And so these devices impact us in our everyday life, whether we know it or not. So the largest market for fiber lasers is actually used in material processing. So this could be metal cutting or semiconductor processing, and it's a decent sized market. So it's expected to reach about $7 billion in the next few years, and it's growing at a rate of around 12% each year, which is pretty much on par with the overall photonics industry. Fiber lasers are also used in medicine for surgeries because they're able to provide precise control and the ability to deliver targeted energy with minimal damage to surrounding tissues. And they're being used more and more by the defense industry for directed energy weapons, and they're also used for different ranging technologies such as LiDAR. So they can be used both for automotive LiDAR, but also for satellite-based LiDAR technologies as well. And one of the main applications for fiber amplifiers is in the telecom industry, of course. So for ultra long haul optical communications, where the signal might be attenuated, so much so that an amplifier is needed to detect the signal. So this is used typically for ultra long haul, such as subsea networks. And the market for such amplifiers is mainly dominated by EDFAs, or erbium doped fiber amplifiers. And that's growing at a steady rate of around 6 to 7% each year. And lastly, it's also been used more commonly now in free space optical satellite communications. And this is either to amplify the signal before it's transmitted, passing through atmosphere, or after it's received, before passing the signal to a fiber network. And that actually brings us to our next point. So what are the advantages and disadvantages of using such devices? And the first point is that they have a high power efficiency. So they actually save energy allowing for power to be easily scalable, which is very important for fiber lasers. They're also compact and flexible, making them ideal for putting them into custom systems or for prototyping. And they provide a high beam quality, stability, and long lifetime. So they have a very narrow line width, and they provide reliable operations, making them ideal for some sensitive applications. So you can see a few here. So nuclear fusion research, they're being used by NIF at Lawrence Livermore National Labs, quantum technologies, as well as they've been used recently for more of these wireless power transmission. Now, they do have some disadvantages as well. They're susceptible to environmental factors, which might be an advantage if you're doing some fiber sensing application. But they also have limited available wavelengths, and they could have higher upfront costs. So they are very well suited for a wide range of research topics and future technologies, not just the mature markets that I mentioned previously. Now, when it comes to modeling the fibers, there's a lot of things to consider. And the first point is doping. So doped fibers use rare earth elements. They could be doped with a single element. They could be co-doped. Or you can have undoped fibers, which are actually doped with some maybe germanium or boron, but not the rare earth elements. And so we'll refer to those types of fibers as undoped fibers in this webinar. And each type of those types of those fibers could be single mode or multi-mode. So now we need to consider that. And then there's a wide range of impairments and considerations that should be looked at as well. So depending on what's important for your system. So that could be mode dependent gain. It could be your doping concentration, doping profiles. You might be interested in four-wave mixing, self-phase modulation, Brillouin scattering, Rayleigh scattering. There's a lot of terms here. I'm not going to talk about all of them, but you can read them. So the main point really, though, is that a simulation solution is really needed to study, optimize, and implement fiber lasers and amplifiers into the systems. So before we get into the technical discussion, a little background about VPIphotonics and who we are. We're a provider of photonic design automation software. We've been around for over 25 years. Our global headquarters is in Berlin, Germany, where Piotr is joining us from. And I'm in our North American office, which is in Rochester, New York. And we like to describe our software using the terms shown here. So it's integrated, it's interoperable, and it's industry leading. So what does that mean? Integrated means that our software solutions are actually integrated together. We have multiple solutions, and they can be used seamlessly. So today we're going to talk about more component design, fiber amplifiers, fiber lasers. But something to keep in mind is that those models can also be used at the system level. So if you're designing, let's say, a satellite communication system, you can actually use your models at the component level in the system level simulation. So our tools are actually integrated together. They're also interoperable. So if you have some custom model that you want to bring in or have some of your own code that you want to bring into the simulation, we enable Python and MATLAB co-simulation, and we're also interoperable with a number of other third-party software vendors as well. And then we claim to be industry leading. So we're always partnering with our customers, with our industry partners, as well as we get involved in a number of the European Commission sponsored research projects. So we're always bringing in what we're learning from those interactions into the software and making that available to the users. So in regards to our software solutions, we do have a very comprehensive set of tools that address different levels of abstraction. So at the very highest level is link engineering. And this is typically these tools are used by internet service providers or equipment vendors to plan and design full optical fiber networks. And then we go down a level to transmission design, which is used to study a specific link. So this can be used for different applications like intra-data center, so AI, machine learning applications, intra-data center, inter-data center, long haul, direct detect, coherent communication systems, satellite communications, LiDAR, and we provide a set of digital signal processing algorithms, and we even get into quantum key distribution as well at that system level. Today, though, we're going to be focused more on component design. And so specifically with VPI Component Maker Fiber Optics to design and simulate fiber-based devices. Also at this level, we do have tools for designing photonic integrated circuits, and we support a number of foundry PDKs. And then lastly, we go all the way down to the device level with VPI Device Designer, where we can calculate, we have different mode solvers, beam propagation method, eigenmode expansion, and we can design different types of fibers. So this could be a multi-mode or multi-core fiber, a hollow core fiber, and do some deep physical level calculations as well there. So we have a comprehensive suite of tools. Today we're going to focus on VPI Component Maker Fiber Optics. And so this tool actually allows you to run simulations with physical fiber models. So not just behavioral or black box models, but the physical modeling. And it supports erbium, ytterbium, thulium doped and co-doped fiber amplifiers, Raman and parametric amplifiers, and it allows you to do a number of different things, such as studying different pumping schemes. So if you actually look at the schematic in the lower left corner, you can see there's the generation of WDM channels that passes through a telecom fiber, so an undoped fiber, and it's actually backwards pumped through this with Raman amplification. And then the signal passes through a doped fiber. It goes through some forward pumping, and it's actually a two-stage EDFA here. So you can play with different pumping schemes. You can really fully customize your amplification strategy here. And this allows you to design not just amplifiers, but also fiber lasers, and look at different optical signal processing schemes, and ultimately study the effects of physics on your designs. So with that, that's a brief overview of the background. And at this point, I'm going to turn things over to Piotr Novik, who's going to start discussing the simulation framework. So Piotr, the floor is yours.
Oh, yes. Thank you, Chris, for a nice introduction. And as Chris mentioned, so now we will start discussing the simulation framework and how our models work in the scope of the simulation framework. To mention first, when we want to simulate some real subsystem or subsystem. So the first step that we need to do, so here, for example, we have a ring cavity fiber laser, and the first step that we need to do if we want to perform the simulation is to decompose this quite complicated system into more simple or atomic components. Then our next step is to find the building blocks provided by our software that will correspond to the building block in our case. And for example, this can be for the erbium doped fiber, we have a model of a doped fiber. For the CW laser, we have a model of the CW laser, and so on. Even in some cases, if there are no modules provided by default by our library, so we provide a co-simulation interface for the users. So this means that this interface allows the users to create their own modules using, for example, MATLAB, Python, C++, and so on. One more important thing, so once we have decided what module do we want to have instead of our real component, we need to specify its parameters. And for example, in case of CW laser, so this module will have several parameters that need to be specified by the users. For example, its output power, its line width, its center frequency, and so on. And once we have decided what modules we want to use and their parameters, so our next task is to combine the modules in the simulation in the same manner that they are combined in the real system. And this looks like a Lego-based approach. So we provide a set of various components, and then using these components and combining them in the different manner, so the user can create his own simulation setup. And now when the simulation is composed, we can try to run the simulation. And when we run the simulation, we use so-called data flow approach to propagate our signal in the system. So what does it mean? For example, in this simple chain, we have module X, and the module X takes the signal and processes the signal according to some algorithm specified by this module. So this can be an optical filter, amplitude modulator, and anything else. Then this module X outputs the optical signal for the next module. Then we have module Y. It takes the signal, and then again, so according to some algorithms that we have inside of this module, it will process the signal, and the signal goes one by one in this module chain. Just one thing that we should mention, that this is just a very simple case when the signal propagates in only one direction from left to right, but also we support bidirectional propagations when the signal can propagate in both directions from left to right and from right to left simultaneously. And now let's talk about what do we mean by the optical signals. For the optical signals, we have several models. And the first and the mainly most important model is the detailed signal model. In this case, the signal is represented with a complex envelope. And you can see an example of the signal in the time domain. And here each point on the time domain plot corresponds to one point that stores information about the amplitude and phase of the optical field at this particular time moment. So that means that this detailed signal model, which is also called sample signals, are represented with an array of complex values. As far as we know everything about the signal, so its phase and amplitude, we can use Fourier transform to get the frequency domain representation of our signal, and we can easily switch between these two representations. And if we want to take into consideration the polarization effects, these signals can be described with a Jones vector, where we store simultaneously the complex envelope for X and Y polarization. But of course, in some cases, and for example, in fiber optics applications, so we are not very interested in the phase of the signal. And this can be, for example, the pump of our EDFA. In this case, mostly what's important for us is the power of the pump and its center frequency. And for this case, of course, if we try to store a lot of information with amplitude and phase, so the simulation can take rather a lot of time. And to solve this problem, we introduced the core signal models. And the first core signal model are parameterized signals. So they represent the discrete spectrum in frequency domain. And in this case, the signal can be characterized with several float numbers: its center frequency, its power, and state of polarization. And this saves a lot of computational efforts and memory and speed up simulations significantly. Also, one more important problem when we model the fiber amplifiers is that the noise produced by the fiber amplifiers is quite wideband, so it can be it can have the bandwidth of several terahertz. And of course, if we try to represent the noise using again the sampled signals, we need to have a very high sampling rate, and again, so we need to store a lot of information. And to solve this problem, we introduce so-called noise bins, and they represent the distributed spectrum. And each noise bin, so in the frequency domain, it's just single pink rectangle, is represented again with its power, its bandwidth, and center frequency. And the state of polarization in this case is described by the Stokes vector. Okay. And now let's talk about the fiber models that we have. And as Chris mentioned before, we have two huge categories: the rare earth doped fiber, which is used as a usual fiber amplifiers or the fiber lasers, and non-rare earth doped fibers. So these are a usual single mode fiber used for the signal transmission between the nodes and so on. All these two categories can be divided in multimode and single mode categories, so which is quite straightforward. So in case of the multimode, the fiber can carry several modes with some non-trivial transversal power distribution, and single mode when the fiber carry only one LP01 mode. And for the multimode fibers, we have static models, and further we will discuss what does mean static. And for the single mode doped fibers, we have two additional models, the static model and dynamic model. And again, further, I will say what do I mean by the static and dynamic models. And for the single mode undoped fibers, again, we have a stationary model and dynamic model. And today, I will show you several application examples with a static doped fiber model and stationary universal fiber model. And now let's talk briefly about the doped fiber modeling and how we approach these issues. So first of all, we will start with some light physical background. And here on the left, you can see the erbium level diagram. And what we can see here is that the erbium ions inside of the fiber has three levels, which are interesting for us. Initially, all ions are placed in the ground state, so they don't have any extra energy inside of them. But using pump at specific wavelengths, so the erbium ions can be excited to the second level using 980 nanometer pump, or directly to the first excited state using 1480 nanometer pump. And then when we have some excited ions, when the ions go back from the excited state to the ground state, they can emit the photons. And these photons can be used to amplify our signal inside of the system. And of course, the higher inversion we have in the system, so the higher will be gain of the system, because so less ions can absorb the photons in our signals. And now let's talk how to describe this mathematically. So in our simple two-level system, we have three main processes. The first one is stimulated absorption of photons when the ions are being excited. And then the photons can relax through the two processes, through the spontaneous emission, and this is not good because the amplifier creates additional noise in this case, and through the stimulated emission, and this is a good process when our amplifier amplifies the signal. And for the stimulated transition rate, we can write down the following equation, to characterize the stimulated transition rate, we need to know so-called emission and absorption cross-section of the erbium ions inside of the amplifier. Also, we have the spontaneous transition rate, and it's reciprocal to the lifetime of the second level. And one more important thing that we need to know to characterize our amplifier is so-called signal ion overlap factor. So this factor shows us how the mode of our amplifier is well aligned with the doping profile of the fiber. And in case if these two quantities are not well aligned, so not a lot of ions will be excited, and therefore the performance of our amplifier will be not so good. And in case, like in this picture, so if they're well aligned, in this case we can get the maximum gain in our system. And now let's write down the rate equations for the two levels. So the first equation is quite straightforward. It says that the total number of ions remains the same. And the second equation just describes the dynamics of the first level population. As I was mentioned before, we have two models, stationary and dynamic model for the doped fiber. And static model means that nothing changes in our system, so everything is in dynamic equilibrium, and that means that the level populations do not change in time. And assuming this, so we can easily find how does the concentration of excited ions depend on the radial position inside of the fiber core. and on the local optical power. And this is very good because now if we know the optical power inside of some specific fiber point, we can easily calculate the inversion population in this specific point of the fiber. And this allows us to write down the optical propagation equations. And in this case, we have the following problem. We know what we put inside of the fiber on the left and on the right. And our purpose is to find out what is the outputs of the fiber on the left and on the right. And for this case, we need to write down this equation that is responsible for the optical propagation. So here we have the term for the stimulated emission and absorption, a term responsible for the loss, and spontaneous emission term. And also we have the boundary conditions. And this problem is called two-point boundary value problem, and this is quite well-known problem, and we have some standard differential equation solvers to find the power distribution along the fiber. And then we can even visualize this power distribution. Okay, and now let's talk about more complex models. Sometimes the lifetime of the third level can be quite long, and in this case, we need to take into account the third level even for erbium ions. In this case, we need to modify the equations. Now we have 3 levels instead of 1. And also we can add one more terms that will describe more complex behavior of our amplifier. So first of all, we can take into consideration the excited state absorption, when the third or second level can additionally absorb one more photon. And also we have terms responsible for the up conversion. This is effect when the 2 ions can interact with each other, and after interaction, so one ion will go back to the ground state and the second ion will go to the higher state. And this is some not very good effects, and again, so they spoil the performance of our amplifier. And in that case, again, so using this nonlinear system of equations, so we can find the level populations and then solve the optical propagation equations. Okay, and just to sum up about our single-mode doped fiber static model, so it supports various doping types, including the erbium, ytterbium, thulium, erbium, ytterbium, and it can work with various signal representations, both with detailed and coarse signal models. And it can be characterized using the Giles or cross-sections fiber parameters. And also it can take into account various higher-order effects, such as the spectral hole burning, concentration quenching, excited state absorption, and many, many more. Also, if we want to take into consideration the multimode fiber, we also have a model for this, and mostly it's very close to the model of the single mode fiber. So the only difference now is that now we have to take into account several modes, and for each mode we need separately calculate the signal ion overlap factors, and also we need to take into account the fact that now these modes don't have the radial symmetry. So now we need to calculate the integrals in a more complex way. But in other cases, it's quite similar to the single mode doped fiber model. And the possible applications of this model is to investigate the multimode fiber amplifiers when we want to reduce the mode-dependent gain. And we can do this by optimizing the index profile, doping profile, and so on. Or we can use this model to simulate the high-power fiber lasers by simulating the core cladding pumping and calculating all necessary overlap factors in this case. And also, we have a dynamic model. As I mentioned, so the static model assumes that nothing changes in time, so the fiber amplifier is dynamic in equilibrium. But sometimes when we, for example, in a WDM system, we drop or add channels, so the system will change its state because something changed in the system. And in this case, the level populations start depend on time. And in this case, we cannot assume that the derivative of the level populations by time is 0. And in this case, we need to take into consideration more complex equations. And in this case, this model can be used to simulate, for example, situations when we drop or add channels in WDM system, and we want to see how much time will it take the system to get in a new steady state in a new steady state. And also it can be used to study the transient effects in such systems and so on. And also it can be used to model the pulsed fiber lasers as well. Okay, and now I will jump to the software to show an example and how it works. So now you should see the software itself. And here you see the schematic that we want to. So this is the simulation schematic that we are using. And here you can see the sketch of the experimental setup that we are trying to reproduce. Also on the left, you can see our module library that provides various models for your real devices. For example, we have a folder called Fibers, and here we can find all fiber models that we have. And you can decide what fiber model you need to simulate this or this specific real setup. Yes, and now I will run the simulation. So, and now we will briefly discuss what we have here. So here we simulate the high-power ytterbium-doped fiber laser, and the system looks as follows. So here we have two pumps on the left and the right, and as an active medium, we have a double-clad ytterbium-doped fiber, and to create a cavity, we have mirrors with a 4% reflection. And to simulate this setup, we need to run several iterations to get some steady state solution. And now we can see how it looks like. So here we can see the output spectrum of our amplifier, and we can see how this spectrum was looking in the beginning of the simulation, and then how it was changing when our signal was traveling in the cavity back and forth. And finally, so here we have some stable output spectrum. Also, we can see how does the output power depends on the iteration number, and we can see that at approximately 30th iteration, so the power doesn't fluctuate a lot, and that means that we found some steady-state laser operation. And also, we can visualize how does the signal travel inside of the fiber. So here we can see that when the signal is reflected on the right side of the fiber, so it's amplified in the beginning due to this backward pump. Then it travels through the fiber without any amplification in the center, and again in the left side of the fiber the signal is amplified due to the forward pump. Then here we have 100% reflection, and again so the signal starts traveling back, so it's amplified in the beginning of the fiber, in the center not so much, and finally the signal is amplified in the end of the fiber, so due to the backward pump. And finally, so here we have 4% reflection mirror, and that means that 96% of laser power leaves the fiber, and the 4% is reflected. And again, so we start the cycle when the signal travels back and forth in the cavity. Okay, jumping back to the simulation. So again, so here is the simulation setup and the simulation results. Also, so we have compared our simulation results with an experimental results, and so our simulation results were in a quite good agreement with experimental results. Okay, and now let's talk about the undoped fiber models. And now we are talking about usual silica fibers that are used to transmit the signals between the network nodes and so on. And again, the problem is quite similar. We know what we put inside of the fiber, but we want to know what is the fiber's output. And to describe the signal propagation in the fiber, we need to use the nonlinear Schrödinger equation. And in this equation, we need to take into account the dispersion effects in the fiber, the attenuation of the fiber, and also we need to take the nonlinear effects. And the nonlinear effects includes the Raman scattering, Brillouin scattering, Rayleigh scattering, Kerr nonlinearity, and many, many more. And of course, if we try to solve this problem as it is, so using this nonlinear Schrödinger equation, we will have the problems because the dimension of this problem is quite high. We will have a 2D grid, so that takes into consideration the time and the position along the fiber. And if we try to solve it, it will be quite hard. And for this, we developed so-called two-step approach to make the problem simpler and to speed up the simulations. And we divided the problem in 2 steps. So at the first step, we replace our signals with their parameterized or time-averaged representations. And at this stage, all effects of counter-propagating waves will be averaged in time. And in this case, we can again solve a 2-point boundary value problem to find the power distribution along the fiber. And at this step, we take into consideration various effects such as Raman gain, spontaneous and stimulated Raman scattering and Brillouin scattering, as well as the relay scattering and many more effects. And once we have found the power distribution along the fiber, we can go to the second step, to the split-step Fourier method for the field analysis now. So the signals are not replaced by their time-averaged representations, but we use the sampled signals, and we calculate how does the fields propagate inside of the fiber, so solving the usual nonlinear Schrödinger equation. And in this case, we take into consideration all phase-sensitive effects such as the self-phase modulation, cross-phase modulation, the Kerr nonlinearity, four-wave mixing, and many more. And so using this two-step approach, we can efficiently solve these equations and find the solution. Also, when we are talking about the modern systems, they are using usually the dual polarization coding when the information is multiplexed in the polarization X and Y. And for this case, we need a bit to modify our model. So again, we need to take into account the Jones vector of our fiber, and to simulate the PMD effect, we are using so-called CoreStep method. In this method, we split our fiber into several subsections, and each subsection has its own birefringent axis. And each subsection introduces its own time delay to the X and Y polarization. And also, when the signal goes from one subsection to another subsection, the state of polarization of our signals is also randomly rotated due to the birefringent effect in the fiber, because this effect is purely random in its nature. And again, then we can use our two-step approach, and now we treat both polarizations separately. And again, using this nonlinear Schrödinger equation, we can find out how does the state of polarization of the signal changes inside of the fiber as well. And yes, summing up, our fiber model supports 2 modes, the scalar mode. In this case, we don't take into account the state of polarization of the signals, and all nonlinear effects are polarization averaged. And this model takes into account the Kerr nonlinearity, chromatic dispersion, attenuation, Raman and Brillouin scattering, multiple relay scatterings, and so on. Also, we have a vectorial mode that additionally takes into consideration the state of polarization of the signals, and it introduces the polarization mode dispersion, polarization-dependent Raman gains, and polarization dependence of various nonlinear effects, such as the safe-phase modulation, cross-phase modulation, and so on. And a very nice option that all these effects can be individually switched on or off. So, for example, we suspect that the spontaneous Raman scattering decreases the performance of our system, and we can easily switch off this effect to check if it was the reason for the poor performance of our system or not. And also, as I mentioned, we have the dynamic model, and this model is used again to study some transient effect in the system. So when the signal variation time is comparable to the transition time of the signal in the fiber. And in this case, again, when we add or drop some WDM channels in the system, so we can see that there are some times when the system is not stable and it goes from one stable state to another. And again, using this model, we will be able to estimate these times and see how does the system performs between these 2 stable regimes. Okay, and now we will show you one more example about the remote optically pumped amplifier. So here you can see the sketch of this system. And here we have a quite long transmission distance of 300 kilometers. And to be able to perform this transmission without repeaters inside of the system, we need to use the remote optical pump amplifier. And it works as follows. So we have the signal on the left side, and we put it in approximately 200 kilometer piece of the fiber. And there the signal is amplified in the beginning using the Raman pumps. Then it reaches the EDFA module. And the pump for this EDFA module comes from the receiver side. Oh, and this pump also propagates in the same fiber as our signal will be propagating after the amplifier. And this allows us to perform 300 kilometer communication without repeaters in the system. And now I will jump back to the software. And here we can see the system that corresponds to this remote optical pumped amplifier. So here we have 10 VDM channels, and each has a power of 0 dBm. And here we have 2 Raman amplifiers, and these 2 signals propagate together in the first fiber span. And in parallel, I will run the simulation. Sorry, I lost the proper file. Yeah. So now the simulation is running, and yes, here we have the erbium doped amplifier, and the pump comes from the receiver side. So here we have 2 pumps. So the first order Raman pump at the wavelength of 1480 nanometers, and we also have the second order Raman amplifier pump to amplify the first order pump. This EDFA pump travels through this piece of the fiber and then reaches the EDFA to amplify the signal we are interested in. Now we have a question. So how should we optimize the system? And are there any parameters that can be optimized to get the better performance of the system? And it turned out that, yes, we have some parameters that we can optimize. So first of all, we can optimize the position of our remote gain unit. So one option, we can place it very close to the receiver, for example, 50 kilometers to get the higher pump and gain in the system, or we can place it rather far away from the transmitter to amplify the signal when it's not so weak. And using simulation, we can investigate both options and see how it affects the signal. So first, let's look at the situation when the amplifier is placed quite close to the receiver and pump. And so currently in this example, the distance to the pump is 50 kilometers. So here we can see the optical spectrum of the signal after propagation in the whole system. And here we can clearly see that the noise in the system is dominated by the amplified spontaneous emission of our EDFA. And one more thing that we can visualize here, we can visualize the output OSNR of our signal. And now we can see that the OSNR in the system is approximately 18 dB. Now we can place the amplifier quite far away from our amplifier. So for example, 130 kilometers. In this case, so the pump is quite weak and it almost doesn't amplify the signal. And now the noise in system is dominated by the spontaneous Raman scattering noise. And again, we can check the output OSNR of our system, and now it's even worse. It's 14 dB. And now this means that there should be some optimum point between these two. And we can easily check this by looking at the OSNR and how it changes when we change the distance from the receiver to the amplifier. And it turns out that the optimum point is 100 kilometers. So at this point, the OSNR figure has the best value, and it is approximately 26 dB. And also we can check the output spectrum of our amplifier. And so now we can see that here we have found some trade-off between the amplified spontaneous emission of our EDFA and the Raman spontaneous scattering in the usual undoped fibers. Also, one more thing that we can try to optimize is the EDFA length. And now I will just visualize results to show them without running the simulation. And again, so here we can check the output OSNR of the signal. for a very short fiber, so 5 meters, and for a quite long fiber, so 15 meters. And again, we can see that for the 15 meters, we have a worse OSNR because the fiber has produced a lot of amplified spontaneous emission. And again, by checking the OSNR figure, we can see that the optimum EDFA length is approximately 8 meters. Okay. Using these simulations, we have optimized the OSNR figure of our system. But OSNR figures says us that our system is quite tolerant to the noise in our system. But one more important effect in the communication systems that must be taken into account are nonlinearities. And to check how the signal is distorted using the nonlinearities, we need to use the sample signals and try to transmit some dual polarization 16-QAM signal, for example. And to do so, we need to use not the fiber optics simulation framework, but the optical systems product. And also we need to do some transmissions between the models. So first of all, we need to replace our signal with a coarse representation of the parameterized signal with more realistic sampled signals, where we store the information about the amplitude and phase of our signals. And in our particular example, we will simulate 10 WDM channels with 28 gigabaud dual polarization 16-QAM signals. One more thing that we need to do is to replace our physical EDFA models available for the fiber optics with some black box amplifier. As I mentioned before, our physical models require the Giles parameters, cross sections of the erbium ions and fiber length, doping profile of the fiber, and so on. And usually for the system level simulations, all this information is not available. What system level simulations use? They use just the gain and noise figure of the amplifier. And using our tool, it's possible to convert such physical EDFA model to a simple black box model by measuring its gain and noise figures. And then we can run the simulation. And yes, everything can be done in the same software. And here we have a more complex system. So as I mentioned, with the QAM signals, they propagate through the same system, but with optimized parameters. And finally, we have a coherent receiver with some non-ideal characteristics. And to compensate these non-ideal characteristics, we need to add a digital signal processing chain, so which includes the modules that compensate the receiver non-idealities, such as the IQ imbalance or some time delays in the system and so on. And also we need to compensate the chromatic dispersion in the system and also compensate the polarization mode dispersion inside of the system. And now, as I mentioned, so we are using the sample signals, and now the simulation takes more time because the signals are quite complex. And I have saved the simulation results just to show them. And yep. So here we can see how does the symbol error rate of our system depends on the power of the channels that we transmit. So here we can see the following thing. So for a low launch power, we have a rather high symbol error rate due to the spontaneous emission and Raman scattering inside of our fibers. So with this low launch power, so our signal is distorted by noise. Then, if we have very high power, the noise is not so relevant anymore, but now the nonlinear distortions of our fiber come into play, and again, the symbol error rate becomes quite high. So that means that we again need to find some trade-off between the noise of our system and the nonlinearities of our system. And so here we have an optimum point of -2 dBm that gives us the minimum symbol error rate in the system. And also, so one more thing that we can do, we can also visualize the power distribution along our fiber link to see how our signals changes along the link. So Here we have two plots. The left plot shows how the our VDM signal, the power of our WDM signals change along the fiber. So here they are just a bit amplified in the beginning of the fiber due to the Raman pumping. Then between these two plots, we have EDFA that gives us approximately 50 dB gain. And finally, here we have the WDM signals in the second fiber span. And again, these signals are amplified in the end of the fiber due to the first order and second order Raman pumps. And finally, we can see this output spectrum of our signals that corresponds to the optimal parameters and the OSNR figure that corresponds to the maximum and the better performance of our system. And yes, jumping back to the simulations, also we can visualize the constellation diagrams of our signals and also try to find even more optimum point for the channel launch power by making smaller step by changing them with, for example, 0.5 dB or even smaller. Okay, and now I give the floor to Chris.
Yeah, thank you, Piotr, for that. And then just to summarize here, as you can tell, the modeling and simulation of fiber-based devices, it's not a simple task. There's a lot of equations, there's a lot of different types of fibers, a lot of different strategies you can use. So at VPIphotonics, what we're doing is providing a set of models for simulating those different types of fiber lasers and amplifiers. And this tool, VPI Component Maker Fiber Optics, also allows for the simultaneous simulation of both doped fiber amplifiers and Raman amplifiers. And then usually it's just not enough to just have the simulation for the fiber-based device, but it's often needed to be simulated in a full system level simulation. And so that's what we provide with our VPI design suite as well. I'll just say that for anybody on the call here, we will offer some free demos and software evaluations if you're interested. So feel free to visit our website or send us an email and we can get that organized.
All right, great. That was such a great presentation. Thank you both so much. So on behalf of Laser Focus World and Endeavor Business Media, I'd like to again thank Chris Maloney and Piotr Novik for such a great presentation, VPIphotonics for sponsoring today's webinar, and of course, all of you too for joining us. Have a great day.